Hello everyone, let's continue the discussion regarding the Lewis structure, and today we'd like to introduce a new concept called AB subscript XE subscript Y notation for Lewis structures. And let's start writing some Lewis structures as the practice. And the first one I want to write about is the carbon dioxide. So it will be CO2. And as we go through the process, first we're going to count the number of valence electrons. That will be 4 valence electrons. You have 1, you have 6 valence electrons. Now you have 2, total 16 valence electrons. Step number 2. Put carbon in the middle, find the middle central atom, and then you have to link them with 2 bars. So you use the 4 valence electron. Remember, each covalent bond needs 2 valence electrons to form. So now you'll have 12 valence electrons. And then you have to satisfy the octet rule from the surrounding atoms towards the central atoms. So for this oxygen, and you see I have 2 valence electrons because of this bond, and I need 6 more. And also on this side, I need 6 more. So I used 12 valence electrons. So now I have 0 valence electrons left, and the step number 3 is done. Step number 4 is take a look at this central atom. Because the oxygen is done, you'll have 8 valence electrons. Now take a look at the carbon. And as you can see here, the carbon has only 4 valence electrons because of these 2 covalent bonds. And that's not going to be happy. One of the things to remember, the carbon, the nitrogen, oxygen, phosphorus, and sulfur, rarely chlorine, and they can form multiple bonds. And actually this has the option of taking the pair of unshared valence electron, the oxygen now, and bring it back into the middle. Now you start forming a double bond with respect to carbon and oxygen linkage. So this is carbon has 8 now, oxygen has 8, and the other oxygen has 8. So this is the correct Lewis structure. And then we can start writing the CH4, the methane, same process for the purpose of saving more time to shorten the Volcast time. And now we're just going to skip all the steps, and we're going to have the correct Lewis structures for methane. And keeps on going, and now we're looking at ammonia. We skip all the steps. Now we have the correct Lewis structure for ammonia. And then we can say, how about water? H2O. The long story short, you will say HOH would be the correct Lewis structure for water. Correct Lewis structure for water. So here I want to get your attention, and what we want to go into star circle is actually not that one. And what we want to circle is regarding to the central atom, how many what we call the electron groups. Now you have this region have 4 valence electrons, and this region has 4 valence electrons. So take a look at the methane. Now we have central atom is carbon. So you have this is a pair of valence electrons shared between carbon and hydrogen, and that one has that one has this, carbon, hydrogen, carbon, hydrogen. So now you go into the ammonia, and you have this, that's a pair, and you have that pair, and a pair is a 4. So now you have water, oxygen, hydrogen, those are 2s, and those are the lone pairs. So here introducing the concept called electron groups. It's electron groups. So those are the ones on the central atom. And they actually have 2 kinds. One kind is what we call the bonded. It's actually forming the covalent bond. The other kind we call it lone pair. Lone pair or lone pairs. And in this case is those valence electrons are sitting on the central atom that's not involved with bonding with another element. So it's kind of 2 kinds. One is those are bonded, there's a form the covalent bond between the central atom and the surrounding atom. And also those are non-bonded, it's called lone pairs. Those are situated right on the central atom, but it's not forming covalent bond with any of the surrounding atoms. So those are called electron groups. Okay, so those are the regions where you'll find valence electrons, either 2 or maybe more. Maybe if you have a double bond, that would be 4. If you have a triple bond, that would be 6. So hence, we're going to today encounter kind of a new concept. It's just literally a little bookkeeping exercise, and this one will be called ABxEy notation. What is being here is A represents the central atom, B represents the surrounding atom, and the E represents lone pairs. Lone pair or pairs of valence electron on the central atom. Okay, so this is a bookkeeping approach, and this is called ABxEy, and the X and the Y, they are subscripts. And those are indicating how many B and how many E corresponding to this do they have. So let's take a look at some examples where we have this CO2, and you're going to have the Lewis structure C, O, and O. And now you have one electron group, 2 electron group. So this one you're going to have is called AB2E0 because there's no unshared pair or pairs of valence electron in the central atom. So there would be, this would be the correct answer for the ABxEy notation for carbon dioxide. And let's take a look at methane. The Lewis structure will be the hydrogen surrounded by carbon is surrounded by 4 hydrogen. This is the correct Lewis structure, and then you'll have 1A, that's the central atom. This is the carbon. Now you have 4 B's. You have 4 B's because you are linked with 4 hydrogens, and also E0 because we don't have any lone pairs on methane and lone pairs on the carbon atom in methane. So now let's take a look at NH3, ammonia. The Lewis structure is and for the ABxEy, we should have A, B. A is central atom nitrogen, B is the bonded, and you should have 3. E, you have 1 pair. So there will be the AB3E1. Move on to the water. You'll have H, O, and O and H. As you can see, they should have AB2 because there are 2 bonded elements, in this case 2 hydrogens with a single covalent bond. Now you will have E2. So this one will be AB2E2, the AB2E2. And if you're looking at a phosphorus pentachloride, you can actually pause. You can actually pause the broadcast and take a look at how you can do it. And now you can restart, and you know what, chlorine will be surrounding the phosphorus. You're going to have the 5 links between the phosphorus and the chlorine. You need 6 surrounding chlorine. So you used up all the valence electrons. And now you check on the central atom, you say, wait a second, it got 10 valence electrons. Well, you know this is the case for the expanded, or sometimes called extended octet, because phosphorus is on the 3rd period on the periodic table. Remember, it has the 3rd principal energy level, which is a principal energy level that is the valence shell. That is the valence shell for the all period 3 elements, and that 3rd principal energy level can hold up to a maximum 18 valence electrons due to the availability of 3D orbitals, so 3D sublevels. So it's the extended octet or expanded octet. So now you will have the central atom, and you will have 5 bonds, and we do not have any of the lone pair of electrons. You can do that on SF6, and you're on S, you're on the F. We're going to write it out like that. You count the number of electrons first, and you will notice this is okay. So this is the SF6, also extended octet or expanded octet, in this case ABxE0. Okay, ABxE0, and you can so now I'm going to really the x plus y, which means the sum of those two subscripts will give you the total number electron groups on the central atom. So this is crucially important. So it's how many bonds you have. That is very obvious for the X, and you got to be very careful about the Y, the number of unpaired electrons. So then this is the one. It's crucially important. Total number of electron groups. And as you can see, the total number of electron groups for NH3 will be 4. And that's for water is also 4. For phosphorus pentachloride, it will be 5. For SF6, it will be 6. Okay, so take a look at the previous one. And for CO2, you will be total number will be 2. For the CH4, the total number will be 4. So those are the electron groups. Those are the electron groups. Let's give you a couple more exercise, and the other one, the other example is BF3. Second example will be boron pentafluoride, and the last one will be a polyatomic ion, IF4 minus. So right now you should pause the Vocast and then work on a separate sheet of paper about this additional 3 problems, and then come back to the Vocast and check the answer. So for BF3, long story short, we're going to have this as the correct Lewis structure for the molecule, and now it will be designated as AB3E0. You don't have any lone pairs on the central atom, but you do have 3 linkages. Remember, this is the exception to the octet rule. Number 1 is deficient on boron. Boron cannot form a double bond, hence it has to stay single bond. So it's kind of trapped with 6 valence electrons. So the BRF5, long story short, and this one will have BR1, 2, 3, 4, 5. As you can see, it's got the lone pairs left. Before I finish up on the others, each one will need 6 to hit the octet. So in this case, you should have AB5E1. So the total number of electron groups should be 6. So total number for that one, boron trifluoride, it will be 3. And if you write all this out, it's actually pretty straightforward. if we bracket it as this one, it actually has 2 pairs of electrons left on the iodine and iodine. So in this case, the notation for that will be AB4E2, and the total number will be 6. So make sure you check the posted worksheet for writing the ABxEy notations for corresponding Lewis structure. Remember, A stands for the central atom, B stands for the surrounding atom, and E stands for the lone pairs on the central atom that's not involved in bonding with another element. With that, let's recap. So if we write the proper Lewis structure, well, we can start getting the information on the total number of electron groups. So first step is writing the proper Lewis structure for either the compound or polyatomic ions or ionic compound. And then start to identify the central atom, what is the surrounding atom, how many of them are, and how many of the lone pairs of electrons, pairs of electrons that are not involved in any of the bonding. So that will be designated by E. Thank you very much for your attention.